Hello, good morning. So I'm here to talk about, yes, the evolution of NEODyS from the beginning till the next evolution to the NEOCC, Neo Coordination Center, in particular because this year is the 20th year that since the beginning of NEODyS. That was born within the team of Andrea Milani, and there were collaborators, well-known collaborators like Steve Chesley and Giovanni Valsecchi and Jenny Saturio. And NEODyS since then is providing the so-called impact monitoring, computes the impact probabilities for NEOs, just discovered NEOs, or maybe NEOs that got new observations from observers. And the main contribution from Andrea Milani was that he introduced the line of variation propagation, and that allowed to improve the computation of the impact probability. Instead of using, for example, 1 million virtual asterisks like for the Monte Carlo, you can reach the same level of probability with much less representatives. NEODyS is based on ORFIT, that is the software tool, a software suite that is operating with the NEODyS and uses several Perl scripts and PHP for the web page. And this is the main one of the main features, that is the risk list. Most of you know very well what is the meaning, and on a daily basis, actually on a hourly basis, we are computing the new impact probabilities, and we posted them into this web page. And that's another example of one single impactor table for one object, that is 2010 RF12. And this is actually the one with the highest probability of impacting late of this century. So, what is inside NEODyS? Okay, it's a database of orbits, but not only orbits, we provide also other data like covariance matrices, residuals, weights, and so on and so forth. We provide tools for observers like ephemerides and observation prediction generation. We provide a list of close approaches with Earth and planets, MOID data, proper elements, and also statistics for each observatory involved in this activity. We provide, for example, a tool that is showing the behavior of the line of variation propagated, for example, in 100 years. And of course, as I said before, the impact risk data is the most important output of this activity. Shortly, how it works. When we have a new orbit, an updated orbit, is going through a scoring system that is triggering the impact monitoring, in the sense that if there are chances that this could be dangerous. So we start with sampling the line of variation along the uncertainty region, let's say. And when we sample the line of variation, we propagate them for 100 years. And then we analyze the close encounters with Earth and to see if there are chances to hit Earth. The problem, okay, starting 2008, our team realized that, it was a team inside a university. And as you know, inside the university, it's very difficult to have a long-term funding of this kind of service. The senior scientists like Andrea Milani and Giovanni Valsecchi were approaching the retirement. So they were worried that after the retirement, all the work that they did in 20, 30, 40 years was going to disappear. And then the team, I was part of the team at that time, involved, didn't have permanent positions. We were all under short-term positions, and the perspective of stabilization inside the research entity in Italy was very, very difficult. Solution in 2008 ESA started the so-called Space Situational Awareness Program. This included also the NEO hazard activities for the NEO segment, and so later on, just to have a longer term position for the people involved, we started a new company that is called SpaceDyS. So last year's in short, related to the ESA SSA activity. Here you see, the funding of the company was in 2011. We started a service level agreement to provide data, service, and consultancy to ESA. In 2015, there was the inauguration of the NEO Coordination Center, and starting 2016, we started the migration of the service from PISA to the NEOCC, and that means that we started to develop and engineer the code for ESA. And the new code is called ASTOD. Now we are approaching the end of the migration. We already delivered the orbit determination functionality, and we just delivered the software a few weeks ago to ESA for the impact monitor activity. And then there were also other activities that were supporting the NEO segment. For the technical evolution, we did a lot of work during these last 10 years. In particular, we did a big effort to automatize the system. So everything is going through automatic processing that are triggered when there are new data from MPC. We introduced the parallel computing that is necessary actually. When I started in 2008, for a single object, the computation was lasting 1 hour and a half, 2 hours. And now in 1 hour, we are able to compute like 20 objects. And that is very necessary, in particular in the view that the increase of new discoveries is going on. We introduced the astrometric debiasing and a new weighing system that is an ongoing process to improve the accuracy of the orbit determination and, of course, the impact monitoring. We introduced also the capability to compute the non-gravitational parameters such as Yarkovsky, radiation pressure, and commutator parameters, together with the orbital parameters, and that is providing the overall covariance matrices that is considering all the parameters involved. We are able to compute also the impact corridor on ground. This is an activity they developed for ESA. We introduced a new line of variation sampling that allowed to increase the completeness level of the that is computed. We also produce a graphic tool for the line of variation propagation visualization. And recently, we introduced also a new service that is called the NeoScan, that is the analogous of Scout at JPL, that is monitoring the NeoCP objects for imminent impactors. And this is a service that is checking the NeoCP on a level of 2 minutes, every 2 minutes. What the difference between the two softwares? Okay, our field it's our Everard Radau propagator. Is using a single step procedure and is adapting when it's going through closer approaches. So it's performing well, but there is no control on the self-style selection and on the numerical error. ASTOD has a different philosophy. It's using a multi-step scheme. So when there is a close approach, there is a regularization technique and a splitting strategy that allows to increase the accuracy of the orbit determination. For the differential correction, in our field, there was a limited level of automation, and we introduced much more automation in the choice of coordinates and the decision for using or not the constraint solution. Future improvements. Of course, the work is not done yet. We need to introduce the ADES data ingestion that is necessary. We need to introduce the post-Gaia astrometric debiasing. We are waiting for the new debiasing using as a reference the Gaia astrometric catalog. And of course, an idea of Andrea Milani was actually to make more automatic the strategy to determine the weight that we put for every single observatory or program involved in this activity through a statistics analysis, for example, using ASTICE data. Of course, we need to migrate to the NEOCC, also other tools like the mode computation, stationary points, and the neoproper elements and ephemeris generation, and so on. impact monitor for other planets. This needs a strong motivation, but and not only, it needs also a lot of resources, but that's up to you. I just want to finish with a couple of words for this person, Andrea Milani. I think, as Juan was saying, that he passed away last November. That was shocking us because it was sudden, was not foreseen. And I think if we are here with a lot of improvements since 20 years ago, 30 years ago, it's also because of him, because he gave a lot of new ideas, new approach for this kind of activity. So we as a scientific community, and as me as a former collaborator with him, I take the commitment to continue to his legacy, because he did a huge and enormous important work for us. So, ciao Andrea. Questions?
So, thank you. So we have time for one very brief question. Anybody? If not, I can ask one myself. Do you have one?
Thanks. What you've done is very, very impressive. Just want to ask a quick question about covariance and how you verify the accuracy of their covariance. What process do you use to do that? And do you find that you need to add some sort of additional process noises or things like that to account for unknown uncertainties?
I mean, the approach is just to use, I mean, the assumption that the error are Gaussians, okay? And then, of course, I mean, you compute the covariance matrices with different coordinates, okay? When the orbit is not very well determined, of course, I mean, the line of variation can be also quite different. And then the choice of the proper coordinates is tricky. Typically, what we use is we use Cartesian coordinates when the object is having a very short arc, but later on we will use equinoctial coordinates, for example. For the control of the error, there are just statistical means, like using the chi-squared and so on.
Yeah, maybe we can talk about this later, but I was really wondering about whether or not you do an overlap test so that as time passes by, you go back and ensure that your covariance assessment at a previous time is consistent with the new observation.
Yeah, okay, these kind of tests are made also for our fit and also for us to see if we're going back and forward, if the results are consistent, and they are pretty much consistent. There is a full test on that. So,
okay, thank you.
So we'll have to move on here, but thanks very much. And